Definition of an arithmetic progression, AP. Hello everyone. In our previous lesson, we spent some time exploring how numbers can follow specific, predictable patterns. Today, we are going to take that a step further by moving from general patterns to a formal mathematical definition. Specifically, we are going to define a very important type of numerical pattern known as an arithmetic progression, or AP for short. Now, let's look at what this actually means so you can understand the concept. At its simplest level, an arithmetic progression is just a sequence of numbers where the difference between any two consecutive terms is always the same. To put this more formally, and this is the part you'll want to remember for your exams, we say a sequence is an arithmetic progression if every single term, starting from the second term, is obtained by adding a fixed number to the term that comes immediately before it. As we move through the next few slides, we will break down exactly what consecutive and fixed mean, and I'll show you some real-world examples to make this crystal clear. Breaking down the definition. Now that we have the formal definition of an arithmetic progression under our belts, let's take a closer look at the specific vocabulary used in that definition. To truly master this concept, we need to break down three key components. First, let's talk about consecutive terms. In mathematics, when we say terms are consecutive, we simply mean they follow one another directly in a sequence without any gaps. Think of it like links in a chain. The first term and the second term are consecutive, just as the second and the third are. There is no skipping any numbers in between. Next, we have the fixed number. This is the heart of the progression. This value is a constant, meaning it stays exactly the same throughout the entire sequence. It doesn't matter if you are moving from the first term to the second, or if you are way down the line moving from the 100th term to the 101st term, the value you add remains identical every single time. Finally, this leads us to the constant difference. Because we are adding that same fixed number at every step, a very important property emerges. If you decide to work backward and subtract any term from the one that follows it, you will always get that same result. This consistent result is what we call the common difference. Understanding these three pillars, consecutive terms, a fixed number, and a constant difference, is exactly what we will use to analyze our savings example in the next slide. Real-world example, monthly savings. Now that we have established the formal definition of an arithmetic progression, let's move away from abstract theory and look at a practical, real-world application to see this concept in action. Imagine a student who decides to start saving money in a piggy bank. In the very first month, the student puts in $100. To build up their savings, the student decides that every subsequent month, they will increase the amount they save by exactly $20. Let's write out the savings for the first few months to see the pattern emerging. In month 1, the amount is $100. For month 2, we take that initial $100 and add $20, which gives us $120. In month 3, we take the previous amount of $120 and add another $20, resulting in $140. Finally, for month 4, we add $20 to that $140, bringing us to $160. Now, let's perform a quick analysis of this data to verify if it meets our definition. First, if we look at the sequence of savings as a list of numbers, we get 100, 120, 140, 160, and so on. To check for a constant difference, let's look at the gaps between the months. The difference between the second month and the first month is 120 minus 100, which equals $20. Next, the difference between the third month and the second month is 140 minus 120, which also equals $20. And the difference between the fourth month and the third month is 160 minus 140, which is again $20. Because this difference remains constant at $20 throughout the sequence, we can confidently conclude that this sequence of savings forms an arithmetic progression. In the next slide, I will show you how to apply this same logical verification to any set of numbers you might encounter. Step-by-step verification of an AP. Now that we have seen how the savings example works, let's look at a more systematic way to approach this. I want to show you a step-by-step verification process so that you can confidently determine if any given list of numbers is an arithmetic progression. Let's work through a concrete example together. Consider the sequence 7, 11, 15, 19, and 23. To check if this is an AP, we follow a logical series of steps. Step 1, we find the difference between the second term and the first term. When we subtract 7 from 11, we get 4. Step 2, next, we find the difference between the third term and the second term. Subtracting 11 from 15 also gives us 4. Step 3, now, let's check the difference between the fourth term and the third term. Subtracting 15 from 19 results in 4. Step 4, finally, we find the difference between the fifth term and the fourth term. Subtracting 19 from 23 leaves us with 4. Now, let's look at our conclusion. Because the difference is consistently 4 for all of these consecutive pairs, we can officially confirm that the sequence 7, 11, 15, 19, and 23 is indeed an arithmetic progression. As we move to the next slide, we will summarize the key takeaways from everything we have learned so far. Key takeaways. First and foremost, remember that an arithmetic progression, or AP, is defined by a sequence where the difference between any two consecutive terms remains constant. This is the core rule you must always look for. Second, it is important to realize that this fixed number we add to each term doesn't always have to make the numbers larger. As we will discuss in a moment when we look at common pitfalls, this value can be positive, which creates an increasing sequence. It can be negative, which creates a decreasing sequence, or it can even be 0, where the terms stay exactly the same. Ultimately, if you take away only one thing from this session, let it be this. The fundamental characteristic of an AP is the constancy of the difference. If that difference changes even once, you are no longer dealing with an arithmetic progression. Now that we have worked through several examples and learned how to verify a sequence step by step, let's pause and summarize the most important points from today's lesson. With these key takeaways in mind, let's move on to some common mistakes that students often make, so you can avoid them in your future calculations. Common mistakes to avoid. First, be careful not to assume that an arithmetic progression must always be an increasing sequence. Many students believe that because we talk about adding a number, the sequence must get larger. However, remember that the fixed number we add can be negative. For example, if you have the sequence 10, 7, 4, 1, and so on, this is still a perfectly valid AP, where the common difference is -3. Second, pay close attention to your subtraction order when verifying a sequence. To find the difference, you must always subtract the preceding term from the succeeding term, that is, term 2 minus term 1. If you accidentally subtract the first term from the second, you might get the correct magnitude, but you will get the wrong sign. Always remember, second term minus first term. Finally, do not let a single outlier trick you. A sequence is not an arithmetic progression if even one single pair of consecutive terms has a different difference than the rest. As we saw in our previous examples, the difference must be identical across the entire sequence without exception. If the pattern breaks even once, the AP is broken. Now, before we wrap up our lesson, I want to highlight a few common pitfalls. Even when you understand the definition of an arithmetic progression, it is very easy to fall into certain traps during exams. With these points in mind, you are now well equipped to identify and work with arithmetic progressions. Great job today!